Welcome, future engineers and architects. Today, we are prying open the black box of production-grade AI agents by examining the internal architecture of Claude Code. We're not just going to look at what this tool does. We're going to treat this explainer like a comprehensive architecture manual. By investigating a system that autonomously plans modifications, runs commands, and adjusts its own outputs, we're going to uncover the exact blueprints you need to design the intelligent systems of tomorrow. Let's get into it. So here is our roadmap for today's explainer. 1. The React engine. 2. The 7-component architecture. 3. Tracing the task. 4. Context and autonomy. 5. Extensibility. And 6. Claude Code versus OpenClaw. All right, let's dive right into section 1. The React engine, the core iteration loop. If you want to understand how execution and performance are truly optimized in these systems, you have to look at the loop driving every single decision. Instead of just spitting out text like a standard chatbot, an agent acts a lot more like a plumber fixing a leak in your house. It goes in, opens up the wall, tests things, adjusts, and then tests again. And it only leaves when the leak is actually stopped. It thinks, acts, observes, and repeats. This fundamental pattern is known as React. And honestly, it's exactly how performance is optimized. By verifying things step by step, the agent avoids wasting time and compute resources going down the wrong path, ensuring every single action brings us closer to the actual solution. Moving right along to section 2, the 7-component architecture, the operational harness. To build that reliable plumber we just talked about, you need some seriously robust infrastructure. I mean, a brain without a body can't exactly fix a pipe, right? Consider the hierarchy of these 7 distinct system components. You've got the user, the interfaces, the agent loop itself, a permission system, the tools, state and persistence, and an execution environment. Get this, only about 1.6% of Claude Code's entire codebase is actual AI decision logic. The other 98.4%, that is all this operational harness. The architecture deliberately isolates the reasoning from the execution. The model decides what to do, but the harness handles how to actually do it, securely. Section 3. Tracing the task, auth.test.ts. Let's ground all this theory with a practical developer task by tracing the lifecycle of a single turn. Imagine you tell the agent, hey, fix the failing test in auth.test.ts. The very second you hit enter, that task gets sucked into a highly optimized 3-step loop. Step 1, assemble context. The system builds exactly what the model is allowed to see. Step 2, the model call, where the AI reviews the info and picks the next logical action. And step 3, execute. The harness grabs that action, runs it through safety gates, and safely executes the requested tool for our auth.test.ts file. Then, the whole result feeds right back into step 1, maintaining a strict, continuous rhythm of plan, act, and verify. Next up, section 4, context and autonomy. Managing constraints and safety. But how exactly does the system balance feeding the AI enough information while not blowing up the memory limits? Well, context is basically the ultimate scarce resource here, and managing it is absolute key to optimizing performance. Instead of just randomly deleting old messages, Claude Code uses a brilliant 5-layer compression pipeline before every single model call. It starts off cheap. Layer 1 just reduces massive tool outputs. Then it snips away the oldest history. Next, it uses microcompact, a process that groups items together to optimize cache memory. If it's still too massive, it triggers a context collapse, creating a quick virtual summary so the model can read it at a glance. Finally, if push comes to shove, it auto-compacts everything by generating a full semantic summary. It's a seamless way of trading a bit of compute power for massive memory efficiency. And this progressive management, it is absolutely fantastic because it protects your data. Even as that temporary context window fills up and gets heavily compressed, the durable storage of your session transcripts remains completely untouched. For you developers out there, that means you can fork, resume, or entirely rewind your architectural state without losing a single drop of ground truth for your project. Now, we have to talk about the human factor. Originally, people thought the best way to keep AI safe was to just ask a human for permission before every action. But the data showed something crazy. Users auto-approve about 93% of permission prompts. Approval fatigue sets in fast, and people literally just start clicking yes without even looking. Because interactive confirmation is practically unreliable, the core design principles had to shift to properly balance human authority with technical autonomy. They adopted deny-first rule evaluations and automated sandboxing, meaning safety holds firm even when the human isn't paying close attention. This underlying tension actually creates a beautifully graduated trust spectrum using 7 distinct permission modes. On one end, you have a super strict plan mode, where the user manually approves every single step. On the completely opposite end, you have the option to bypass permissions entirely, offering almost total autonomy. But even with maximum autonomy turned on, there's an unbreakable safety net, a machine learning classifier operating quietly in the background that can proactively block risky shell commands, even when standard rules would have let them slide. It really is a perfect architectural balancing act. All right, Section 5, Extensibility via hooks, expanding the agent. As systems engineers, you'll inevitably need to know how developers can securely extend this architecture using custom plugins or rules. The execution loop actually exposes precise injection points, which we call hooks. You've got a pre-tool use hook, which lets you intercept and block a tool call before it even happens, perfect for enforcing corporate policies. There's a post-tool use hook to mutate a tool's output before the AI even sees it. And then stop and subagent stop hooks let you forcibly halt the React loop. By offering these specific points, you can inject custom policy logic right into the execution pipeline. Finally, Section 6, Claude Code versus OpenClaw, the impact of deployment. To really master system design, we have to contrast Claude Code with an open-source system called OpenClaw to understand how the deployment context fundamentally impacts the architecture. Just look at how their trust models and resource management differ. Claude Code is this ephemeral command line tool. It only lives as long as your terminal session and relies heavily on per-action safety checks. OpenClaw, on the other hand, acts like a persistent multi-channel gateway. It secures the perimeter first with identity and access controls, and only then lets the embedded agent act. Claude Code treats the agent loop as the center of the universe, whereas OpenClaw treats the gateway as the center. It's fascinating how product requirements completely alter the system scope. Yet, despite these massive architectural differences, both systems converge on one surprisingly beautiful simplicity: their memory. They both completely avoid opaque, complex vector databases. Instead, they prefer using totally transparent, text-based markdown files like cloud.md and memory.md. The agent literally opens these text files, reads the instructions, and jots things down for its future self. It just goes to show that even the most advanced AI agents in the world still run on simple, rock-solid plumbing. The design space for AI agents is vast, and it's evolving incredibly fast. We've seen how execution loops drive action, how context compression pipelines optimize memory, and how permission modes secure autonomy. So, as future systems engineers, which bottleneck are you going to prioritize? How will you balance autonomy with control and complexity with simplicity in the architectures you build next? Keep these blueprints in mind, and thank you so much for joining me to unpack this architecture today.